The term fluid motor is normally used to identify those devices which deliver continuous rotary power output when supplied with fluid under pressure. The term motor is sometimes used by manufacturers to denote reciprocating cylinders. Technically, this is a correct usage but can lead to a misunderstanding of the type of actuator to be used. For the remainder of this video, we'll use the term motor to describe a continuous rotating device. Whether to use a cylinder or fluid motor depends upon its application and the type of load to be moved. At first glance, it may seem that cylinders are the better choice. For applications where either can be used, a cylinder is typically less costly compared with a fluid motor of the same horsepower. Cylinders have leak-tight, non-metallic piston seals, which will give a consistent performance at very slow speeds against a wide range of load resistance. Fluid motors, on the other hand, have metal-to-metal internal surfaces which use a small amount of leakage for lubrication purposes. A cylinder with leak-tight seals can be operated over a wide range of speed, under changing loads, and with reasonably consistent performance. A fluid motor can only perform similarly if it's designed with precision tolerances to reduce its natural internal leakage, which increases cost. Cylinders also produce smaller pressure spikes, called hydraulic shock, when stopped suddenly. Fluid motors tend to produce a much larger amount of hydraulic shock if stopped suddenly due to the momentum energy contained in their rapidly rotating loads. Finally, cylinders are much more efficient than the typical fluid motor. Energy loss can be held to about 5% in a well-constructed cylinder. But fluid motors or pumps experience power losses from fluid leakage and friction within the device. These losses can be anywhere from 10 to 25% of the input power. However, despite all of these setbacks, fluid motors are advantageous due to their complete rotary motion and the ease with which their speed and direction can be controlled. On most fluid motor applications, it's necessary to have a motor which can accept high pressure on either port so that the motor can be reversed. In all hydraulic devices, a small part of the high-pressure oil will slip through clearances between the gear sides and the housing and will collect in the seal and bearing pockets. If not vented, these pockets would soon be exposed to the same high fluid pressure as the ports, which can then dislodge the shaft seal. To prevent this from happening, several motor construction methods are used. The first method creates an external case or housing drain. The seal and bearing cavities are internally joined and vented through a drain port. Another method to prevent fluid buildup uses internal check valves. These valves allow accumulated leakage to flow in a specific direction to either main port, but will prevent backflow of high pressure into the bearing and seal pockets around the shaft. Finally, high-pressure shaft seals are utilized to minimize the consequences of high-pressure fluid exposure. These are mechanical seals in which two lapped surfaces run against each other to seal the shaft. A rotating surface, called a seal ring and typically made out of bronze or graphite, is pressed against a stationary surface called an insert, which is typically made out of steel. A spring ensures that the seal ring presses tightly against the insert. A packing, or O-ring, ensures there is no leakage between the spring and seal ring. Internal hydraulic pressure ensures the two surfaces are held in tight contact, but even this method is not leak-tight, and weepage is a common occurrence. Additionally, the lapped surfaces are sensitive to contaminants in the oil, which are abrasive and cause leakage to increase. Fluid motors have many advantages over typical electric motors. An electric motor can be prone to overheating, especially if it experiences higher than normal loads. Fluid motors, on the other hand, will simply stall and come to a stop if they are overloaded. Once the motor stops, the fluid begins to cool down. Additionally, unlike an electrical motor, fluid motor speed can be made responsive to its fluid temperature. If a sensor detects an increase in fluid temperature, the speed of the motor can be directed to reduce. Due to their advantages, fluid motors can be the ideal choice for conveyors, hydraulic transmissions, fan drives, vehicle drives, cable reeling or winching, and many other industrial applications.